All right, so first thing, we're going to be wrapping up chapter 1 today mostly. I might say a couple of things next Tuesday. So make sure you are reading to the end of the chapter. So today we're going to kind of cover more structure of the atom, and then don't forget that you have the modern materials discussion to do. So once you sign up for a group, reply to, there should be 3 replies off of the main thing. Don't reply to the main thing, but click on the one that is for the that particular topic, and then you should be able to reply. So any questions about stuff coming up? All right. Some of the stuff from the previous chapter, or what we did on Tuesday. So one of the things that we looked at was finding things on the periodic table. So as kind of a review, what element is in group 13, period 4? So group, remember, is the columns. Group 13 has boron at the top, right? All right, so what do you think?
Looks like gallium.
It's gallium. Now, if you had been thinking it's the one that's In and not gallium, remember that with the periods, we count from the sides. So even though boron doesn't have anything in the first period, that's still the first period. So boron is in the second period. So that's something to pay attention to. Okay, if we are looking at gallium, then would we say gallium is a metal, a non-metal, or a semi-metal? So it fits into the metal category. So remember that diagonal brown area on our periodic tables, or the zigzaggy line that's drawn on some of your periodic tables? That's what tells us where the metals and the non-metals are. So this dark blue area, it's almost a black color there. Those are metals. The blue ones, purple ones, orange and red, all of that are metals. Okay. And then what do we think? Is it solid, liquid, gas? It's probably a solid, with the exception of what metal? Mercury is the liquid. Okay. We're going to go here. So on the front page of your notes, it asks you about the difference between metals, non-metals, and semi-metals. And so we can look at a metal and kind of know that it's a metal because it sort of looks metallic. So what is metallic? Kind of shiny. Usually it's some variation of gray, though we do have like the gold or brass or copper that have a little bit of color in them. They don't have a whole lot of color, but they're shiny. But that's not 100% true of all metals. They're not all solids. But what is true of all metals is that they're all very good conductors. So our best conductors, you probably can't see this, but this is silver and copper. Those are our best conductors. Okay, so these are really good conductors. Tungsten's not a great conductor. And so it's only, what is that, maybe about a third that of these other two. But if we compare it to silicon, and we know silicon's in microchips and things like that, so it has some conductivity. Silicon isn't very conductive at all. It doesn't even show up on this chart. Okay, so the main feature of a metal is that it's very conductive. Now, what we're going to do for the next graph is kind of zoom in on tungsten and silicon, and then at the very end is carbon. So this graph on the left-hand side here is showing tungsten really tall and not even all of it. So this goes up to 10,000. So this is only showing up to this point. If we zoom in on just this area, then we can start to see the carbon showing up here and not silicon. So carbon's actually a little bit more conductive than silicon. And you might think, well, why then don't we use carbon? Well, carbon is conductive only in 2 dimensions. So remember when we were talking about allotropes, we said carbon had diamond and graphite. So this is the graphite, and it has these layers, and those layers can slip and slide on one another. So that made it a good lubricant. Electrons can move across these layers, but it's really hard for those electrons to go from one layer to the next. So that makes carbon a little bit more difficult to conduct electricity in 3 dimensions. So you may have at some point in your life had a club or maybe a science teacher who pulled out a pencil and used that to conduct electricity somehow because there's graphite in there, but it's moving along just that 1 dimension rather than trying to go in all sorts of directions. Also, if you've ever used a mechanical pencil, graphite tends to break pretty easily, whereas wires tend to be more malleable. Okay, so nonmetals compared to metals, far less conductive. And our semi-metals are a little bit more conductive in one of their forms. Our semi-metals have 2 or more allotropes. So remember, allotropes are forms that they can take depending on how they're bonded together. And one of those forms is a terrible conductor, and one of those forms is a little bit better of a conductor. And then maybe they have other forms as well. All right, so if we look at other nonmetals, far worse than silicon and carbon and things like that. All right, so those are the key distinctions there. So the big picture is that metals are conductors in 3 dimensions. They can conduct electricity every which way. Semi-metals have one form that's an okay conductor in 3 dimensions. And non-metals like carbon, the best they can do is conduct in 2 dimensions. And really carbon's the only one that's really a great conductor in 2 dimensions. Okay, next slide is a little bit of a review. This isn't bad. We talked about we can use the periodic table to know what charges of things are. So here in the middle in the transition metals, there's just lots of different things. So you don't have to know these. The point of this part of it is just to show you, you can't just memorize it. But group 1 always has a +1. Now notice it just says plus. It doesn't have the number next to it. Number 1 is sometimes invisible in chemistry. We just don't write the 1. Okay. The column 2 has a +2. Now, if you're on the 3rd page of your guided notes, there's a little chart there. So if you look at group 1, so you can just write column 1, the name for that is the alkali metals. And group 2 has a very similar name. It's not alkali, it's alkaline earth metals. So alkali refers to the pH scale. So the pH measures how acidic something is. And if something is very acidic, it has a low number. If it has a high number, we say it is alkaline, or we sometimes use the word base. Okay. So I'll probably do a demonstration on Tuesday next week to kind of illustrate how those are alkaline. And they're both metals. And then we know this forms a +1 and this forms a +2. So those are some characteristics. Our alkali metals are very soft. These you can cut with a butter knife. That's how soft they are. So if you try and imagine, you know, cutting through a chain on a bracelet or a necklace with a butter knife, that would be pretty difficult to do. These are super, super soft. These are less soft. These are highly reactive, whereas group 2 is slightly reactive. So I told you that we'll pretty much never see group 1 out in the wild in nature as a pure element. You're not going to find a lump of sodium because it's so reactive. It's always going to form that +1. The alkaline earth metals, sometimes you can find them as being in their just metallic form. So this is a ribbon that is made out of magnesium. So I can touch and hold it. It's not burning me or anything. They do tend to form a little coat on the outside where the outside reacts a little bit with the air. And if I left this for centuries in the back of a closet, it would probably disintegrate, just like you can imagine a rusty nail over time disintegrating completely. But they're only very slightly reactive until you get down to the low. Okay, so those are some characteristics of those. And then on the other side, we had group 17 and group 18. 17 is called halogens. So gen means to make. So when that's in a scientific words, it means that you're making whatever the prefix is. And the prefix here refers to salt. So sodium chloride is table salt. But for scientists, things that have a metal and one of those elements, all of those would be considered salts. pretty much ionic compounds they call salts. So halogens, what charge do they form? Group 17. Remember? When you looked up on your periodic table from yesterday?
-1.
-1. Okay, so fluorine forms -1, chlorine forms -1, bromine forms -1. When they are negative, we change the ending to I. We'll get back to that later. So we don't say sodium chloride, we say sodium chloride. We would say F- is fluoride. So the halogens, remember those are all diatomic. And they are all non-metals. And then group 18 we know as what? Last column, noble gases. And these hoity-toity gases don't want to get together with anybody, even with each other. And so they don't form diatomics and they don't form ions. So their charge is always 0. Okay, so they are inert is the word for not reactive. Our domains of chemistry, as a reminder, is just a way of thinking about a chemical either as the thing that is in front of us, like an ocean of water or solid ice. Symbolic is using the letters and the numbers. So it's really tiny here, but H2O for the molecular formula, and then a G, S, or L for the phase. And then particulate is how we're showing those molecules interacting. So we're going to see that for some other things. So as a reminder, the gases are not dense because the molecules are far apart. So that's one difference. And they're moving really fast. A solid is going to keep its shape. That's its macroscopic property. And it does that because all of the atoms are really close together. And if I were trying to illustrate that I have a solid as opposed to a liquid, I would have some kind of vertical edge here to show that it's not flowing all the way out. Whereas with a liquid, I'm going to illustrate it going all the way across the whole scene. And then it's going to be level at the top because it's not going to pile up, it's going to flow. So solutions, some characteristics is that if it's water-based or if it's made of gases, it's going to be clear. So we can see through these, we can see through water. The contrail here isn't what I'm showing. The air is clear, but how do you show air? So the air is clear, that's a solution. This would be heterogeneous because it's cloudy, but the air itself is a solution. And then if it's not liquid or gas, if it's solid, then if it's made of metal and not an element, then it's going to be a solution, right? So brass is one solution. What's another mixture of metals? Can you think of any? Gold is an element. Silver is an element. Bronze. Bronze is also an alloy. Remember, that's the word for a mixture of metals. So that would be considered a solution. Okay. And a solution is another way of saying homogeneous. Heterogeneous, I think of as being chunky, like a chocolate chip cookie. But if we've got water-based, it might be cloudy. It might be opaque, so we can't see through it. So here, this is cloudy. We can't see what's behind here because there's so much in there. It's a little bit see-through. You can kind of tell whether there's light behind there, but there's enough solid suspended in there that we can't tell what's going on. For heterogeneous, we're looking for things that are cloudy or opaque. Sometimes it's not going to be super obvious, so we want to think about, is there more than one phase? So if I see both a gas and a solid, smoke is a case like that. So the air is the gas, but the little dust particles or ashes in the air, that's what's making it smoky. So that's going to be 2 different phases. That makes it heterogeneous as well. So each of these pictures, each of these scenes is showing the same phase. What phase are these in?
They're all gaseous.
They're all gaseous. So the particles are separate from one another. And then we've got these kind of streaks showing that they're going very fast. So in each of these cases, I only have one color inside of there. So one color, what is that telling me about the elements? It's the same element, right? So in this case, they're individual atoms. This might be a noble gas. And in this case, they're pairs. And what would we call it when the atoms pair up as an element? Starts with a D. Diatomic. So these are both elements. Even though this has molecules, they're both elements. Okay, so that's something to remember. in this scene, I have, it's a little bit hard to see, the blue, 3 blues on the outside of each of these and kind of a gray, almost black in the middle. But every single one has 1 of the grays and 3 of the blues. Okay, so what am I looking at there? It's not an element. Is it going to be a compound or is it going to be a mixture? It's a compound because all of the particles are the same. So since this has 1 black and 3 blues, this has 1 black and 3 blues, that has 1 black and 3 blues. If I knew what the elements were, I could write a chemical formula for it. This then is going to be a mixture. Now, if it's gases, no, we can't tell whether we can see through it, but all of those are gases. There's no solid or liquids in there. That's going to be a solution. So we'd say that's a solution or homogeneous. Most elements are not found as pure elements. They're found combined with other elements. So we would call these minerals if it's just 1 compound, or ores if it's a mixture. Okay. So this is the mineral olivine. And this mineral is found mixed in with other things. So you can see some darker splotches in here and some green spots here. So when it is pure, then we call that a mineral. And so that would be a compound. So minerals are compounds, and they'll have a chemical formula. But if it is a rock or an ore, then we would say it's a mixture. Usually they're heterogeneous, but rocks are going to be mixtures. Okay, so this is heterogeneous. We can actually see the different, there you go. You can see the chemical formula. So for aluminum, we find this iron that is hematite. Sometimes you'll find hematite as the those magnetic rocks you can buy at gift shops where you can buy strings of them and stuff. Silicon is found as silicon dioxide, and that's one we'll talk more about as sand or glass. All right, and if I were going to do domains, macroscopic would be a picture of the olivine. Particulate would be trying to show the different atoms. So I have iron here and here. I have magnesium here. I have oxygen here, and then silicon right in the middle. So it's actually got lots of different elements in it, not just the silicon. Okay, so those are 3 different domains. Oh, and then the symbolic would be this. Okay, next thing we're going to do is look at an atom. All right, so you're going to fold it so that when you fold the majority of the writing on the inside, from the bottom and from the top, it's going to look like you have an S here. And then what we're going to be able to do is make flaps for each part, the charge, the Z, and the A. So that's what the cutting will accomplish. Okay, so it should kind of look like this, with 3 things at the top and 2 things at the bottom. So an atom, and this is something that I'll probably ask on a quiz or a test, is draw a simple atom and label the parts. So I've got 3 major things I want to illustrate. 3 subatomic particles. So in the middle, I have, the whole thing's called the nucleus, but I have the protons and I have neutrons. And the protons are positive. What charge do the neutrons have? They're neutral. So the neut tells us they're neutral. And then our electrons are negative. And the electrons kind of go around the outside. Sometimes people will draw a circle. Sometimes they'll draw them kind of in ovals like this. You'll see that as the symbol for an atom, just showing its 3-dimensional kind of thing. But that's our basic structure. Okay, so we know where things are. We know the names of them. And when we say nucleus, we know this is the nucleus. Okay, but we don't usually draw atoms when we're talking about them. So if we want to talk about a particular kind of atom and tell what those parts are, we can kind of put that together in a symbol, and that symbol is going to look like this folded piece here, okay? So this is called an isotope symbol, and it has 4 parts. So X is going to be the element symbol from the periodic table. So if it's carbon, I'm just going to use the capital letter C. If it's potassium, I'm going to use the capital letter K. Some rules about those symbols. The first letter is uppercase or capital. So you're not allowed to write like a lowercase I for iodine. That doesn't count. The reason is it gets confusing when you're smushing them together in formulas as to where one thing starts and one thing ends if you don't follow these rules. So the first letter is uppercase. If there's a second letter, is lowercase. So if I had this, and this, they would all represent different things. They all say COS, but this is cobalt and sulfur. This is carbon, oxygen, and sulfur. And this is carbon and osmium. Okay, so using a lowercase for the second letter really helps to tell when we're starting on a new element. So sometimes if you're writing out a formula or something and you're using all capital letters, that's more common than all lowercase. If you're using all capital letters, I might count off half a point for that reason. Okay, so let's talk about, so this is where it says, the middle top part here, this is X stands for. Okay, so X stands for the element symbol, and the text formatting, first letter is always uppercase, second letter, if it's there, is always lowercase. All right, I'm going to go to Z. So Z is in this bottom corner here. You fold this flap, you'll see Z. So where it says what it stands for. Z, the name for it is atomic number. So on the periodic table, it's the whole number that appears in the box. So 1 for hydrogen, 6 for carbon. We look underneath hydrogen, lithium has a 3. That's its atomic number, okay? And what it's called and its definition are kind of the same thing, but what it's equal to is the number of protons. So in my drawing, I drew 2 protons. So Z would be equal to 2. Make sense? So where it says purpose, the purpose, since each element has its own atomic number, the purpose is to tell us which element we're looking at. Now, this also tells us which element we're looking at, so it's kind of the same information from both of those. So sometimes Z gets left off. But the purpose is to make it absolutely clear which element we're talking about. All right, so Z up in this box up above says Z is equal to the number of, you're going to write protons there. And then the Z can be found, you know, I borrowed this from somebody else. It can be found in 2 locations. It is in the lower left corner of the symbol, but it's also found on the periodic table. It's in that box on the periodic table. So if you're trying to figure out what is it for this particular thing, you look on the periodic table. All right, and then A. So now we're in the top corner. So A's name is mass number. But I want you to pretend like mass isn't there. So it's called the mass number, but it doesn't have anything to do with mass. It has a little bit to do with mass. But don't think of it as a mass. It's more like a weight class than a mass, okay? So we're not actually weighing anything with the mass number. The way that you get it is to count up how many protons and neutrons there are. The sum of protons and neutrons. And then in the box below, the math for it, A is equal to the number of protons plus the number of neutrons. I mean, kind of saying the same thing. The purpose for this is to distinguish between two atoms of the same element that have different numbers of neutrons. So it helps us to tell the difference between a carbon with 8 neutrons and a carbon with 6 neutrons. Those are called isotopes. So this is an isotope symbol because it helps us to distinguish atoms that have different numbers of neutrons. And I know this is kind of low for people there, but what I just wrote, I'll actually write it up here too. Carbon 12, 6 versus carbon 14, 6. All right. 99.9% of carbons are this carbon 12. And carbon 13 and carbon 14 chemically behave the same. They're all going to end up in carbon dioxide. They're all going to end up in sugar and in fats and all of those things. But carbon 14 is radioactive. That over time, and it takes several thousand years, it starts to decay and turn into nitrogen. And so what we can do is we can tell how long it's been since something's been alive by looking at how much carbon 14 is in it. Because as long as it's alive, it's gonna, be eating or breathing or whatever, getting more carbon in it and replacing it. But once it dies, that all starts to decay and turn into nitrogen. And so you have less and less and less of it. So if you've heard of carbon dating, you can carbon date something by looking at how much carbon 14 is in it. So if you're taking your grandmother's antique desk to the Antique Roadshow and they tell you, oh, this desk was actually just made 20 years ago, and you're like, no, we kept it in great condition. It's 400 years old. What they could do is they could take a sample of it and see how much carbon 14 is in it. And if there's very, very little, then that would show that that is much, much older. That makes sense? Kind of? Okay. We'll get into more of how that works in chapter 4, I think. So don't worry about how that works now. Just know that there are different kinds of carbon. All right. So the last thing that is on there is the charge. So any particle that has a positive or a negative charge is called an ion. Okay. How do atoms become ions? What changes about these particles to make them ions? The electrons, yeah, they're on the outside. And the nucleus is teeny, teeny, tiny. If this whole wall were the size of an atom, the nucleus would be about the size of this dot. So this nucleus is really teeny, teeny, tiny, and the electrons are way out there. So really easy for those to pop off or sometimes to gather more. Okay, so charged particles have gained or lost electrons. So the atomic number, Z, on the periodic table tells us how many protons there are. If the atom is neutral, it tells us how many electrons there are. But if it's charged, we can figure out how many electrons there are from the charge, or if we know how many electrons, we can figure out what the charge would be. So let's see. Charge tells us the gained or lost electrons. So if I have a negative charge, I've added the negative thing. So for a negative, we have gained electrons. If it's neutral, electrons equal protons. And if it's positive, I have lost electrons. Where did I put it? In your packet, you should have something that looks like this. That should be the next page after the one we've just looked at. This should fit right here. So you can tape it there or you can glue it there. Whatever makes you happy. And at the bottom, you'll see where it says Battle of the I words. So we've used 2 I words. We've got isotope and we've got ions. So the ions are the charged particles. They're positive or negative. The isotope is going to be, it has varying numbers of neutrons. And is it Tatum? Is that right? What's your question? I ended up with extras and I was like, why do I have extras? So anybody else missing one? All right.
What do we put for agriculture?
For isotope, the isotope has differing numbers of neutrons. So it says isotopes are atoms with differing numbers of neutrons.